Okay, good morning or good afternoon, everyone. And in this lecture, we will be covering our drug metabolism and our drug-drug interactions. So first, here are our learning objectives. And let's start first with why does the body metabolize drugs? So the main purpose on why our body metabolizes drugs is that our body is designed to protect itself from foreign substances. And examples of these foreign substances is our drugs. And the way our body protects itself is through metabolism. So the goal of metabolism is very simple. It is to make the drug more polar. So when the drug is more polar, it cannot cross the blood-brain barrier or the cell membranes, and it is more suitable to go into the urine for faster excretion. Hence, metabolism influences the duration of action. Usually, the duration of action becomes lower. Drug activity also becomes lower. And in some cases, toxicity actually goes up. Most of the time, it goes down, but in some cases, that metabolite is toxic. And it also plays a part in our drug-drug interactions. So here are the consequences of metabolism. So we usually have a shorter duration of action. So we have a shorter effect. In terms of activity, once a drug is metabolized, it usually becomes inactive. However, some drugs do become active in the case of prodrugs. In terms of toxicity, some metabolites are harmful, but these are only some. And for drug-drug interactions, we will talk about them later. Okay. Now we have two major phases of metabolism. We have our phase one and we have our phase two. So these two phases of metabolism, they go hand in hand. They do not go consecutively, but they go one after the other, meaning they can happen at the same time. We have two phases of metabolism. We have our phase one and we have our phase two. For phase one, you can call it our unmasking. Usually, this removes certain parts of the structure or it alters certain parts of the structure to make the structure more polar. Okay, so common examples of which is our oxidation, our reduction, and our hydrolysis. So this alters the structure. Most of the time, the goal is to make the part of the structure amenable for attachment of more polar compounds. Next, we have our conjugation. So when we have our conjugation, it simply is the attachment of highly polar groups. So once there is a suitable site for these groups to attach to, these reactions will now occur, like glucuronidation, sulfation, and acetylation. The major common enzymes in the body is our CYP450 system. I'm not saying that these are the only enzymes present, but these are the most common. These are present everywhere, and most of the drugs will be affected by the CYP450 system. So the major CYP enzymes comes from our cytochrome P450, and the major ones CYP3A4. This is the metabolizer of most drugs. CYP2D6 for our CNS active drugs. CYP2C9 for our NSAIDs, and CYP1A2 for our aromatic compounds. So later, I will discuss the roles in drug metabolism when we talk about our drug-drug interactions. Now, for the structural basis of metabolism, we're not going to talk about it in a biochem way, but we're going to talk about it in a structural way. So we're going to predict metabolism. Primarily, we have a framework here where we can identify functional groups, where in the exact functional group our enzyme will attack, what reaction will take place, and what would be the probable metabolite. the effect and the optimization on how to fix our metabolism. Okay. So where does metabolism occur? Which part of the structure does metabolism occur? Here are some common sites. We have our benzylic allylic carbons, alpha carbons next to heteroatoms, electron-rich aromatic positions, and our exposed alkyl chains. Okay. Now, when our enzyme attacks, they don't attack functional groups per se. They attack specific atoms within those groups, and they tend to attack the common targets stated earlier. These four right here. For our CYP enzyme, these are the most common targets because these are the targets that can be metabolized. So let's start with our benzylic and allylic carbons. So when we say benzylic, this is a carbon next to a benzene ring. Take for example, we have a benzene ring right here. This is an benzylic carbon. Okay, so this is a carbon next to a benzene ring because it is one carbon away from a benzene ring. When we say allylic, it is a carbon next to a double bond. So this is carbon of a double bond. This is carbon of a double bond. This is your allylic carbon. Okay, let's draw benzene again. This is your benzylic carbon. Okay, so why are they attacked? They are attacked primarily because once they are oxidized, these positions can form stabilized intermediates, meaning they are stable enough so that the forward reaction proceeds. The benzene ring or the double bond can delocalize electrons, such as resonance. They can temporarily hold the electrons so that they could rearrange. This makes oxidation energetically favorable. So, take for example, we have ethylbenzene. This is our benzylic carbon. This will become oxidized. What would happen is it would form an alcohol. Here on the screen is an actual drug. This is tolbutamide. Can you look for a benzylic carbon? So this is not a benzylic carbon because this is a sulfur. This, on the other hand, is a benzylic carbon. It would be turned into an alcohol. Next, we have terbinafine. Terbinafine, this is the affected part right here. Or you could also have this. This one is near a double bond as well. So the key takeaway here is if a carbon is next to a double bond or benzene, it is weak. Next, we have alpha carbons next to heteroatoms. So heteroatoms, such as nitrogen and oxygen, these are rich in electrons. So carbons directly attached to oxygen or nitrogen can be oxidized. They are attacked primarily because nitrogen and oxygen donate electron density and makes the adjacent carbon more reactive. And it also facilitates bond cleavage. Oxidation of the alpha carbon leads to O dealkylation and N dealkylation. Take for example, we have ether. What happens here is this carbon is the alpha carbon next to a heteroatom. What would happen is this would split. It would form R, OH, and formaldehyde. Okay. since it is an oxidation reaction that would occur. Okay, so in diphenhydramine, these two are probable areas in which it would be attacked. So this is an alpha carbon next to nitrogen, to oxygen, and this is an alpha carbon next to nitrogen. If we have O, the alkylation, this would be split, this would be converted to OH, and this would be split up. So how it works is that aside from being polar, it splits the structure, rendering it absent in its pharmacophores, leading to non-binding. For amines, these two are alpha carbons. However, the reaction for amines is N-dealkylation. So N-dealkylation simply removes one alkyl. So it forms R, N, H, CH3, and the loose one here, probably another aldehyde. So it loses one methyl group. So if you see a nitrogen or an O and a single carbon attached to it, there could be that could be a target for enzyme attack. Next is electron-rich aromatic groups. So this occurs on benzene with high electron density. So take for example this one. So if you have the ortho and para position, this is ortho, this is para. If the benzene has high electron density, this too would be attacked. How can you tell if a benzene has high electron density? If the ring has one of the following substituents. So what makes the ring electron rich? We have our OH, NH are our alkyl groups. So take for example, let's have a phenol-like structure. So this is number one. So it would be attacked at the para position, this one. So this carbon would be oxidized. And what would happen is you would have a dihydroxybenzene system. Another example is toluene. So it could attack at the ortho or the para. Ortho, meta, para. So it could attack here or attack here. Okay. So next we have our exposed alkyl chains. So what it is, these are simply carbons that are exposed, meaning they don't have uh, bulky neighbors. and they could easily be attacked. So typically, these are carbon chains that are free or in terminal ends. They are attacked primarily because they are accessible, meaning there is no steric hindrance and these are easy to oxidize. And the typical process is simply stepwise oxidation. So an alkane, for example, it would become an alcohol. And after being an alcohol, it becomes an aldehyde. And eventually, it will become a carboxylic acid. Like for example, if our propyl chain, the terminal carbon is easily attacked, provided that there is no neighboring compounds. Take note that if it is branched, metabolism slows, meaning if, like for example, CH2, CH2, CH3. So this is a single chain. Sorry. 1, 2, 3. 1, 2, CH2, CH2, CH3. 1, 2. If it is like this is more resistant to our metabolism. If on the other case it is bulky, something like this won't be attacked because benzene adds bulk. So here's the summary. So what happens at the site of metabolism? So for aromatic rings, so this is just the summary of the metabolism earlier. For the aromatic rings, it is hydroxylated, meaning you attach hydroxyl. For benzylic and allylic, you have oxidation. For ether, you break the chain using O dealkylation. For amines, you have N dealkylation. And for our alkyl chain, we have our oxidation. Okay, so for aromatic rings, you simply add OH. For allylic or benzylic carbons, it becomes a, okay, this one, it becomes an alcohol. For ethers, the ether part becomes an alcohol and the other part becomes an aldehyde. For amines, it works for secondary and tertiary amines. You remove a methyl group. And for alkyl chains, you have oxidations. Becomes an alcohol as well. But it can also proceed to other functional groups. Okay, so what happens to the metabolite and the effect? So the common metabolic outcomes is increased polarity, decreased lipophilicity, increased elimination. For possible effects, you have increased activity for prodrugs, and probably toxic metabolites. So for optimization, how do we combat metabolism? So for some strategies, we could block the metabolic site, add hindrance, add fluorine, or replace functional groups. For blocking the site, you could simply add bulky groups. You could substitute or add bulky groups to prevent the enzyme from reaching it. Another approach is you could add fluorine. CH can be oxidized while CF cannot. CF cannot be oxidized. That is why in our bioisosterism, replacing hydrogen with fluorine is a good step for preventing oxidation. However, you cannot add too much fluorine because it could alter the charge of the structure too much. And strategy 3, you could replace the functional group. If, for example, ester is rapidly metabolized while an amide is much slower. So it renders it slower to hydrolysis. Okay. We have our drug-drug interactions. So when we say inhibitor, it is when your drug slows down the enzyme. When we have inducer, your drug increases the enzyme. And when we have substrate, your drug is the target of the enzyme. So typically, drug-drug interactions is you have an inhibitor drug plus a substrate or an inducer drug with a substrate. Remember that the substrate is the drug that is affected. Okay, so take for example, so we have a substrate for CYP3A4. If you give a drug with an inducer, if you give a drug that is an inducer, what would happen to the amount of enzyme and what would happen to the duration of action? Okay, so if you have an inducer, the amount of enzyme increases, the duration of action of the substrate decreases because it is more metabolized. If you have an inhibitor, the amount of enzyme decreases, the duration of action increases. However, it could also account for toxicity as well. Now, for the case of prodrugs, the opposite is true. Since prodrugs need to be metabolized first before it has an effect, the effect is different. So if you have an inducer, the amount of enzyme increases, but the duration of action increases or the effect increases. And if you have an inhibitor, if you have an inhibitor, the amount of enzyme decreases and the duration of action or the activity also decreases. Okay? And lastly, we have non-CYP metabolism. These are less common than our CYP, but they are also important. So these are the metabolism pathways for drugs that has these compounds. So key enzymes here is our esterases, our amidases, our MAO, which is our monoamine oxidase. This is important for our CNS drugs. and our UGT. It's just the enzyme responsible for glucuronidation. Okay, so that ends our lecture for today. Thank you for listening and have a nice day.